So WebGL is based on OpenGL ES2, which was the OpenGL specification designed for mobile phones, smartphones, tablets, things like that. Obviously, with the rise of smartphones in the last 10 years, people have been wanting a more and more immersive and a richer experience. So along came OpenGL ES, and then on top of that, with the trend in abandoning plugins for browsers for various reasons, it was felt that a standard rendering technology for within the browser needed to be developed, and the result of that is WebGL. So the idea of this workshop is basically just to give you a sort of a gentle introduction on WebGL itself, how to get started, and eventually how to get a textured quad on the screen like we've got here. So as you can see, it's just a very simple quad, just made up of two triangles with an image of the WebGL logo. And that's the entirety of what we're going to do this evening. There will be more tutorials, hopefully planning on running one this time sort of every 2 weeks. So the next one will be on the 13th of November, no, 12th of November, I believe is the date. And that'll be going to into much more depth about shaders and color and things like that, how we can do some extra effects and cool things. But with all that sort of out the way, oh, just one more note. The workshop is sort of designed with the understanding that you at least either have an understanding of programming or have done some programming before. I'm not going to go into loads of detail about HTML or JavaScript or anything like that. It's purely focused on WebGL. So hopefully you can still get some benefit from it. So yes, so let's go and take a look then at how exactly we make this rotating quad. So this is our index.html page. Now this is obviously not going to be too unfamiliar to anyone who's ever put a web page together or done any HTML. So it's a sort of a very simple page. We're not doing anything clever at all. We just set a title. We've set some meta tags to do a bit of housekeeping, make sure it's the correct size on mobile devices and it's responsive. And then there's two JavaScript libraries that I feel are pretty much invaluable when you're doing WebGL. And the first of all is jQuery, which is sort of kind of widely regarded as the way JavaScript should be. It just makes selecting elements from the DOM and animations and things like that just much easier. And the next one is GL Matrix, which is a JavaScript equivalent of the GLM library. If anyone here has done any OpenGL, they may be familiar with GLM. And the idea behind GL Matrix is basically it just takes all the hassle out of manipulating matrices and vectors. I have no desire to do all of that hardcore maths myself. So yes, so I use that to kind of deal with it all myself. And then just underneath, we link in our own CSS style sheet and we link in our JavaScript. And that gives us an extremely exciting white page. Obviously, this is to be expected. We haven't done anything. So what we need to do is to add in some content into the body. Now, WebGL relies on the canvas tag, which was brought in with HTML5, which means that you do need a browser that can support HTML5 and WebGL. This isn't so much of an issue nowadays because all of the major browsers, Internet Explorer, Firefox, and Chrome, they all support WebGL and HTML5, even down to a number of older iPod and iPhones and Android devices. So it's a really good idea to perhaps consider WebGL as the technology you're using if you're targeting mobile or if you perhaps want to have an interactive experience within your web page. So what we need to do then is add in our canvas tag. And if we take a quick look back at what we've just done, we will see that there is now a 300 by 150 pixel canvas. That's the default size in Chrome. It doesn't automatically fill up the size of the container it's in. So we want to go and add in a container to wrap it around. And what we want to do is just in our CSS, we want to make sure that it's all full screen. not sure what that flashing is, so I'll take that out of full screen mode anyway. So we want to just take all the padding out of our HTML and body, and also set the width and height to 100%. And then we want to do exactly the same thing for the container that we've got. So then if we pop back and refresh this, you'll see that that container now takes up the entire screen size with our canvas within it. Now the canvas, again, as I said, it doesn't automatically stretch to 100% width and height of the container it's in. We'll handle that in a little bit. So that's the sort of the main bits out of the way for the DOM. For the moment, at least, there's nothing more that we need to add into our index page. We've just got a simple div that fills the full width and height, and within that we've got a container. We've got a canvas. So what we want to do is we want to pop over to our JavaScript file, and we want to use jQuery to call a number of functions once the page is finished loading. So we just use this here to do that. And the first thing we need to do is we need to initialize the canvas. So we'll create a method here quickly to do just that. Just double check that's the correct name. And so then we go and select our container, and then follow it up with selecting the canvas. Now ordinarily the jQuery selector returns an array, and if it's an array of just one element, any methods you call on that selector will go straight to the first thing. For whatever reason with a canvas that doesn't work, so you have to just choose this this zero selector just to get that first element out of the array. We just check that we've actually managed to get the canvas, and if we haven't, we'll just pump a little message out to the console. We return false out of that, and then we can continue. So if we modify this slightly so that it doesn't continue processing if there are any problems. Okay, so we've found our canvas, and now we want to change the canvas width and height. Remember before I showed that it was only 300 pixels by 150, and this is very easily done by literally just setting the width and height to the width and height of the container. So if we just put a little debug message in here, and another one in here, we can check we're actually making progress and these are being called. So if we refresh this, you see that we're coming into these methods, and if we now go and take a look at the canvas, you see that it's now the full width and height of the container that it's wrapped in. Okay, so that's the canvas bit dealt with, and let's return true out of that, obviously. So once we've got our canvas, we now want to actually initialize WebGL. So we'll create a method called init WebGL. We'll pop down here and actually call it. So we need a global variable called GL. Now this is what's going to hold our actual WebGL context. And if anyone here has done any OpenGL development on desktop in sort of C++ or anything, you're probably aware that trying to get an OpenGL context is a bit of a ball ache. You've got to deal with rendering contexts and device contexts and checking everything worked and then selecting the correct profile. Don't need to do any of that with WebGL. The browser handles it all for you. So all we need to do is just tell it that we want to get a WebGL context. And to be on the safe side, some browsers still refer to it as experimental WebGL. I've not noticed any issues with selecting it like this. It still had the same feature set in the browsers I've tested it. And just as a matter of prudence, let us just double check that that's actually worked. And we'll return false if it hasn't. So we'll pop back to our our web page here. You see it's initializing WebGL, and we've not got an error message. So we can continue. Now the first thing we want to do is we want to set up a few properties within WebGL. Just like OpenGL, WebGL is just a big massive state machine. So if you set a property and never change it, it will remain that way. So what we want to do is set the color that the screen will clear to, or the frame will clear to, at the beginning of each frame. For the most part, this doesn't really matter, because in a 2D or a 3D game, chances are you're going to fill the entire screen with your sprites or your models or your skybox. But in a simple thing like this, it's important that you know that the frame is actually rendering. So I dislike using white or black simply because they're just very, very abrasive. So I use a sort of a dark grey, and all I'm doing here is just passing an RGBA value. So 0 being sort of black, 1 being white. So for red, green, and blue, I'm just passing in 0.2, and then the alpha value 1.0. And then we'll just go ahead and clear the actual screen. So GLClear takes a number of parameters. Well, takes a parameter of which can be a number of things that you can OR together. So we tell it we want to clear the color buffer, and it will clear it to that color there. So if we just pop back again to our web page, you'll see it's now gone to the dark gray that we've set. And just as an example, if I change that to that, we should now get a sort of a reddish color. There you go, which is absolutely horrific to look at. So we'll put that back to our gray. Now we also need to sort of set up how we're going to handle if two polygons are, in front of each other and one's behind another. We use the depth buffer to that, so that if you rendered a polygon 10 units away, and then you render a polygon that's 20 units away, it ensures that the one that's closer to you is in the correct place. So we just want to enable depth testing and pass in what the depth function is that we want to do. So that sets up our depth buffer and the way that it's going to work. And we'll just double check here quickly. It's gone back to our gray. We've not got any error messages. WebGL is very helpful that if you do something wrong, it will tell you very quickly that you've done something wrong. Obviously, if you're used to, again, OpenGL on the desktop, you can spend a fair bit of time hunting down, trying to find a problem, or you might just get sort of an instant crash. Again, beauty of doing it in a browser, it gives you loads of information. So that's initialized our WebGL. So what would normally take a couple of hundred lines in C++, we've done in 48 lines. It's just much simpler to do WebGL. The next thing we need to do is we need to actually go and set up our scene. We want to decide what it is that we want to render. And once we've initialized our scene, we then need to actually render the scene. So we'll create another method called initScene, and we will call this down here as long as nothing goes wrong. And what we'll also do here is tell it to start to render the frame. So all the major browsers provide request animation frame. Ordinarily, you'd have a thing like a game loop or just a very tightly wound loop that runs as quickly as possible, trying to push as many frames to the screen as possible. If you do that in a browser, you're likely to get the browser on Windows, it will sort of grey out, you won't be able to close it and things like that, because it will execute on the main user interface thread. So by using request animation frame, the browser knows to call this method here whenever it's painting the window and sort of whenever it has time. So we'll just pop back up here. And do that quickly. So we'll draw the actual scene in here, and at the end of the scene, we'll tell it we want to draw it again next time. And at the beginning of the scene, at the beginning of the frame, we want to clear the buffer bit and we also want to clear the color. We'll just pop back in here quickly, just check there are no error messages. Brilliant. So now we've effectively set up everything for it to sort of immediately start rendering. For all intents and purposes, this is rendering now. Depending on the power of your PC and things like that, it will be set there at a nice sort of 60 frames a second. Typically, you'll find that WebGL context within a browser will be limited to the VSync of the monitor, which, to be perfectly honest, is absolutely fine. So we'll want to come back to our init scene now. We actually want it to draw something. So in the good old days of OpenGL, you used to use a thing called immediate mode and the fixed function pipeline. In immediate mode, you would just constantly send vertices with some color information and normal information, and the GPU will take that and draw it onto the screen. So that's been done away with now in sort of newer versions of OpenGL, and in OpenGL ES2, you can't do that at all. You need to provide a vertex buffer, and the same is true for WebGL. So what we want to do is within our scene, we want to initialize the buffers. So we will go ahead and create that method. And we need to actually go and start to put some data into a buffer and generate it. So the first thing we're going to need is we're going to need a global variable up here, and we're going to call it Polygon buffer. If my antivirus would go away and stop popping up saying it's updated, that'd be great. So to create a buffer, it's really not difficult. You literally just call gl.createBuffer. You don't need to pass in any other parameters. That's it. And we want to go ahead and bind the buffer. Now this is a vertex array, so we pass in array buffer as the first parameter, and then we pass in the buffer that we've just created as the second parameter. Now we need to give this buffer some data. So this will be our actual vertex data for the quad that we're going to put on. So I typically tend to do all of my rendering in triangles. Most 3D modeling packages output in triangles and things as well. And it's easier to visualize a triangular polygon. Your GPU will break it down to triangles anyway, even if you submit quads. So we want to pass it some data. Now we do that by passing in just a plain old boring array. And we define this static draw. What this means is that the driver, the WebGL, the OpenGL driver can go off and take the data once and then just ignore it. It will sit resident on the graphics card, or potentially resident on the graphics card, and it won't attempt to try and keep it in sync with your system RAM. If you had vertices that were changing every frame or quite often, you'd want to make this a dynamic array, and it just means that the driver can optimize the way that it stores the data. So we need to create this vertex array even. So we're just going to very simply just do a normal plain JavaScript array. Now a vertex within the 3D world is 3 components, X, Y, and Z. So what we're going to do is we're going to pass in some vertex data. So you'll see we've passed in 6 vertices, which is 3 vertices for 2 triangles, and you'll see they obviously share 2 corners, which will be the top right-hand corner and the bottom left-hand corner. Now we need to remember that there's going to be 6 elements here because we can tell OpenGL that in a little while. So our initialized buffers is pretty much done. We've created a vertex buffer. We've generated our array that we're then going to pass to GL. We've bound the buffer that we want to put our data into, and then we've actually gone and passed that data to GL. So if we come over here quickly and take a quick look, again, absolutely nothing's happening. We've still not told it to actually draw, and there's a few other bits and pieces that we need to do first. So that is shaders. So again, in the good old days, you could use the fixed function pipeline, which would handle everything for you. Nowadays, you have to provide your shaders, and these are programmatic bits of code that sit on the GPU and execute. Now, for the most part, there are two types of shaders. You've got a vertex shader and a fragment shader, sometimes referred to as a pixel shader. Now, the vertex shader will be called for every single vertex that gets sent to the GPU, and the fragment shader will be called for every pixel that is generated and put onto the screen, ignoring the depth buffer bit. So if you render a pixel behind, you may well find that your fragment shader gets called as well. So you want to try and reduce that as much as possible by sorting your scene geometry, but that's far down the line. So we need to come in here and create our method for shaders. Now, ordinarily in a sort of a proper production game, you would load your shaders from text files asynchronously, just like you would any other model data or texture data or audio data. However, for simplicity, what we're going to do is we're going to drop it right into the DOM just here. So we're going to create two script tags, one for the vertex shader, one for the fragment shader. And to ensure your browser doesn't try and go and actually execute this code, we're going to give them different types. So we're going to say the type here is X shader, X vertex, and this one here is fragment. So GLSL, which is the shader language sort of typically used with WebGL, is very C-like. So you end up with a main function, if I could type, for both. And these will just get executed. Now you can have other functions within your shaders that get called from within main and things like that. But for this very simple one, we will just keep it exactly as it is. So for the vertex shader, all we need to do is we need to take in the vertex that's passed. We want to transform it into world space and then pass that off to the GPU. So GL position is a built-in variable. This is the output that you use to say exactly sort of where that vertex is within world space. And the way you do that is you take the incoming vertex, which will be a vertex, you multiply it by the model view matrix for that object. That is what you would use to move your object around the scene. Obviously, models that are output from a modeling package, all the vertices are within their local space or the object space. So you use a model view matrix to actually move them around the world. And then your projection matrix is what actually sort of defines how your camera looks and how your screen will then render it. So we need to pass these two things in, or these three things in. So what we've got here is we've got two uniforms. Now a uniform is anything, excuse me, is anything that gets set into a shader and it just stays the same for every iteration of that shader. An attribute is what changes for each invocation of the shader. So our two matrices will stay the same for the entire of our quad, but this will then iterate through all 6 vertices within our array. So we need to take that as an attribute, put these as uniforms. And then coming down to the fragment shader, we literally just want to output a color for the moment. So let's just output white. So I said that GLSL is very C-like. It has a few extra specific data types that C doesn't have, primarily matrix and vector-based things. So for example, you've got a 3-component vector here, or a 4x4 matrix. And there's the built-in maths required for multiplying these together. So coming back to here, we're just passing it a 4-component vector, so it's R, G, B, and A. and we're passing that to the built-in variable GL frag color. And this just says this fragment color is white. That's all we need in those for the time being. If we pop back over to our init shaders function here, we need to grab this source code out of the DOM. We need to compile the two programs, then we need to link them together into a shader. So if we go and grab the source code, and again we'll use jQuery for that, which makes it very simple. So those two variables should now contain the source of vertex shader and fragment shader respectively. Now we need to give ourselves another global variable, and just like we did with the buffer, we need to ask WebGL to create us a program. So a program can be linked together from multiple shaders. It doesn't have to just be one file per vertex, one file per fragment, but you can only have one main function. So again, just like C or C++, you can have multiple source files that link all together, but you still only have the one entry point. So we create a shader, and then what we need to do is create each individual sort of shader itself. Now these don't need to hang around, so these are perfectly fine to be local variables. All we need to keep is that shader, as we'll reference it later. And we need to actually then go and pass the source code. So we take that and the source, and we compile the shader. So at this point you'd normally do some error checking. Just for the sake of brevity, I'm going to miss that out and hope that nothing goes wrong. But you can check that the shader actually compiled, and if it hasn't, you can go and get the compilation log and actually work out sort of which line and what the error actually is. But again, for brevity, we'll miss that out just for the moment. So there we have it, two compiled shaders with the source code from our index.html here. Now we need to link these together into our shader program that we've created here. So what we want to do is we want to attach them to the shader. And again, as I said, you could do this as many times as you want for each sort of shader type that you've created, as long as you've only got the one main function for each. And then we need to link the program. Again, there is a way for you to check this and retrieve the link log if for whatever reason this doesn't work, but I'll miss this out just for the moment. And now if that's all gone through fine, we need to actually go and bind that. As I said before, WebGL is a state machine. You set something, it doesn't change. So since we're only using a single shader, we'll just set it to use the program here, and then we can sort of almost forget about it. So we have these three variables, and we need to pass in some data to those. So what we need to do is we need to find the location within the shaders for each of those variables, similar to in sort of C or C++ or other programming languages where you get a pointer to a variable. We need to go and grab the pointers to these. Now I quite like to store these into an array each. So we'll go and grab a vertex first, which is what will be the actual vertex attribute that's passed in for each iteration. And we need to enable that location as well. So we just pass it in the value that we've just gotten out, and that's brilliant. That now means we know the location of this attribute. We've enabled that location as well, and later on we can then tell it where the data for that is. And if we just grab our two uniforms quickly, and we go and store those into our array. So we've grabbed the attribute location and we've enabled it, and we've grabbed these two uniform locations. You don't need to enable uniform locations. So we just need to grab these out of our shader. So as long as everything's gone okay, we shouldn't get any error messages. Brilliant. So that means our shaders will be being compiled, otherwise you'd see an error message coming through saying that this wouldn't be valid. And now we can move on. So if we head to our draw scene, and just bear with me 1 second. So we've cleared the screen. We've already bound the shader up above because we needed it in order to grab those attribute locations and things. Ordinarily, if you had multiple models, they may well have separate shaders. You might have different shaders for your UI, for your models, for post-process effects. So you need to make sure that you bind those before you use them each time. Now we need to go ahead and actually set those two uniforms and the attribute. So first of all, we want to bind the buffer that we created earlier that contains our vertices. And we need to tell it where to actually put that data. So we grab that back out. We'll tell it that there are 3 components per vertex, that it's a float type, and a couple of other parameters. These last two allow you to create an offset and a stride. So if you wanted to include vertex data in the same array as normal data and texture coordinate data, you could do it all through here and just tell it to jump each iteration. And if we go ahead and do draw arrays, we're going to draw some triangles starting from 0 in the vertex array. We're going to draw 6 vertices. Now this goes back to our 6 vertices here, so it will start here, boom, 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 boom. Next time it comes around, it will start again from the top. So we need to set these two uniforms here, but we've not actually created a variable for these yet. So if we pop back up here, and we will create a projection matrix, and we'll create our model view matrix. And then we can take these to our draw scene, and we can also pass these to the shader. We do that by calling specific uniform methods based on the size. So if this was a 3x3 matrix, this would be matrix 3. It's of type float, and V just means that you're going to basically give it the first item in the array. It effectively is a pointer to the array. So we want to pass in our projection matrix, and that will get passed in as a float 32 array. Same with our model view matrix. So this now sets those values within the shader. If for whatever reason you were passing in other data, whether it be your texture coordinates or something else wacky that you were going to do within the shaders, this is how you pass that information along. For example, say you had lights in a scene, this is how you could pass in a bunch of information about each light. Brilliant. So in theory, that should work. However, we've created these and they're both just identity matrices. This isn't going to help us at all. We need to actually set up a proper projection matrix. So there are 2 major projection matrix types. You have perspective, which means that objects that are at a distance are, appear smaller than an object of the same size closer to you. It's what we see. It's what's used for a 3D camera. And then you've got an orthographic matrix, which is basically it's sort of a square matrix. If something is 10 units away and something of the same size is only 5 units away, they'll appear as the same size on the screen. And this is really good, obviously, for 2D games or user interfaces and things where the distance from the camera shouldn't change the size of the object. So if we pop back to our init scene quickly, and we're going to go ahead and use a nice built-in function to, to GLM. I'm going to say we want to create a perspective matrix. I'm going to pass it into that. And we're going to have a vertical field of view of 45 degrees. We need to get our aspect ratio, and the easiest way of doing that is just to take the canvas width and height, and we've already got this stored as a global variable, so we can easily access those. And then we need to set the near and far plane. So the near and far plane is what causes clipping, basically. Object that is further, in this case, an object that is further than 1,000 units away won't be rendered. An object that's closer than 1 unit won't be rendered. And because these are positive numbers, it means that the negative z-axis moves away from you. So if you want to, if your camera is at the origin at 0, 0, and you wanted something that's 10 units away, you'd say that its z-axis is -10. And we need to have a quick little look at putting this function together. If I can remember which way around it is. And that just converts degrees to radians. And that will then go pump this into there, and we've got our projection matrix. What we also want to do is make our model view matrix, because if we leave it as identity, then the model will be rendered at 0, at the origin at 0, 0. So that's not going to help, because 1, we wouldn't be able to see it because it's clipped, and 2, well, that's just not very interesting, to be honest. So let's move it further away, and we'll do this in our init buffers section. Sorry. Now, there's probably an easier way to do this with the GL matrix, but this is what seems to work for the moment. So we create a 3-component vector. We set that vector to be 0, 0, -5, and then we want to translate our model view matrix. So this will create a model view matrix that equates to a translation of -5 in the z-axis. And this is again what we're passing in here. Passing in the projection matrix. We've assigned all of these. So in theory now, we've told it to draw 6 vertices. In theory, we should, if we pop back here, probably get lots of error messages. Ah, no. That's me getting ahead of myself, assuming I've done something wrong. So you see now we have a quad on screen. It's the color white, and it's 5 units away from the screen. Just to demonstrate that that is actually being set by the shader. Let's say we change it to that, and you'll see it's now a cyan color. If we put that back to there, we will go and get our white quad back. So that is the sort of the bare minimum required in order to sort of draw a quad to the screen. You'll notice that because we're in a perspective matrix, that the sort of 0, 0 of the screen is dead center. And because we defined our quad as 0, 0 to 10, 10, the origin is in the bottom left. I would say if you were doing a 2D game, you may want to put the origin in the middle of the sprite, in the middle of the quad. So, you know, you would make it -5 to +5, x and y, to set the origin to be in the middle. Or you can do a translation beforehand, make the rotations, move it back again and things. So that's got our quad rendered, and you'll see that it's not too dissimilar to what we have here. What we want to do is let's add this rotation in. Just get that out of the way quickly. And we want to do that each scene. And we're going to use the model view matrix for that. So we're going to have to tell it we want to rotate it on the y-axis. It's the model view matrix that we want to change. We want to change it by 0.01. That will update every frame. Let's see what happens. And you'll see this now starts to rotate. It's definitely not at a ridiculous high frame rate, otherwise you'd see this whizzing around. But as I said, anything above 60, you're sort of wasting in a browser anyway. So it's better to have a nice smooth rate here. So yes, so that's gotten that rendering to the screen. Now we need to start thinking about how we're going to do our texturing. Now we obviously can't include an image directly in the DOM like we have done with the shader, so we're going to have to go and load it. So if we create another method, and let's call it init textures, and I can't type. And we want to call this when we do our sort of initialize our scene as well. So we'll just stick that in there. So we need now a global variable, just like we had for shader, for the texture. And we go and ask GL to create us a texture. So we have the benefit of the fact that we are in the browser. We don't need to go and get a library to load an image and decode the PNG or the JPEG or anything like that. If it's an image that a browser can load, then you can get access to it. The easiest way to do that is to create a new image class, tell it what to do on load, and then pass it the location. So I've gone ahead and created an image folder, and within that I've got a WebGL logo white.png. So this will go off and tell that image to go and load that source. And what we want to do is, because this is going to execute asynchronously, once the image is finished loading, this is where we want to do all of our loading of the texture. We've already created the texture here, so let's go ahead and bind the texture now, in case you had multiple and something else had gone and sort of switched the active texture. And we need to go ahead and set up a few properties. So tell it to flip on the y-axis. We need to pass it the actual texture data, which is going to be in an RGBA format, and it's an unsigned byte. And we just pass in the image. Again, we don't need to go into this image and actually say, give me where, the actual byte array or anything like that. We literally just pass the image, it's taken care of for us. And then we need to set a couple of parameters for how the filters are. So in the shader, you'll access a thing called a sampler. Now, a sampler is a texture plus a number of filtering modes and properties. And the two that you require, there are others, but the two minimum are minification and the magnification filters. And this basically determines what texel to choose within a texture based on how close to the screen it is. So if it's if a texel is smaller than a pixel on the screen because of how far away it is, that's your minification filter. If a texel is bigger on the screen than a pixel because it's close to the camera, that's the magnification filter. And we want to tell it what to do in that situation. And in both these cases, we're literally just going to say, use a linear filter to select the correct texel. And then we go and unbind the texture, just to keep things clean. Now, because this loads asynchronously, what we need to make sure is when we're doing our draw scene, that we don't try and draw this texture before it's actually loaded. So we'll just do a sort of a quick true-false boolean to determine whether this is loaded or not. And once we're in the onload, we know it has, so we just set it to true. And then down in our draw scene function, we want to say, before we bind everything, if the texture is loaded, we want to say that in the texture slot 0, because you can have multiple textures bound at the same time. Say you wanted to have a diffuse map and a normal map. And in that slot, we're going to bind the texture that we have. Ooh. And correct that typo there. And what we also need to do is, just like we've passed in these two to a uniform within the shader, we need to do the same thing with the actual sampler itself. So we will have a variable within our fragment shader called uSampler. We need to tell it that the value of that is 0, and this corresponds to the texture unit 0, which is what we're currently bound to. So we need to go and update our fragment shader to have that uniform. Do that just by adding in uniform. Again, it's set once at the beginning. It's a 2D sampler, and we're going to call it sampler. Now we want to go and grab the texture from that, the color from that, which is going to be a 3-component color. It's just RGB. And the way you do that is you simply do something like this. And select the RGB out of it. Now you'll see here that I've used this V texture coord value. So we need to get that as well. Now because it's going to be passed to us from the vertex shader to the fragment shader, it's what's referred to as a varying. Now if we put that in there and that in there, that means that anything we write into V texture coordinate chord in the vertex shader is going to load in the fragment shader. Now that's not exactly true. I mentioned earlier that the vertex shader is called for each vertex iteration, and then a fragment shader is called for each fragment or pixel. What the shader will do, and it's quite clever, is that whatever we put into this texture coordinate will actually get interpolated to the appropriate fragment shader. So say you've got two vertices, one at 0, 0 and one at 0, 1, and you're on the fragment that's exactly halfway between. It will interpolate the value that you've put into texture coordinate between there, and this helps us to choose the correct coordinate based on the only 6 coordinates that we're going to have. So we simply just write into here the attribute value that we're going to pass. So just like we've passed in an attribute for the vertex, we're now going to pass in an attribute for the texture coordinate. And this will get passed off onto here, and then we will pass this into our vec4 here and just set the alpha to 1. So take the sampler, take the texture coordinate, grab the RGB values and put them into this variable, and then that's what we pass out to frag color. So now we need to work out how we're going to pass in these coordinates. And it's exactly the same as we've done before. We're going to create another buffer, pass in some data. So if we pop up here quickly and go to that, we'll create a Polygon texture buffer. And we'll create another one. Now these need to have the same number of elements in. So we've got 6 vertices, so we need to have 6 texture coordinates. So we'll duplicate that one up, and we'll duplicate that one. And then we're going to come in here and we're going to bind that buffer and pass it the data. Again, this won't be changing frame by frame, so we can set it as static, and the driver can decide what to do with it, whether it puts it, whether it keeps it in system memory or whether it makes it resident in the GPU. And that's it for sort of generating that. We need to then, just like we have done elsewhere, we need to duplicate this code here, but we'll do it for a texture chords, which I believe is what I've passed in. Nope, just a texture chord. And we need to enable that there. So we've grabbed our vertex attribute and our texture coordinate attribute, we've enabled both of them, and we've stored the value into our shader attributes array. Brilliant. So we load our texture, we create a texture, we create a texture coordinate array, and we pass that in as well. And the next thing we need to do then is change our draw scene ever so slightly to actually take this into account. So we've already made it so that it only binds the texture if it's there. Next thing we need to do is bind the texture buffer, and we need to pass it that pointer again. So I'm going to say a texture coord there. Now texture coordinates only have 2 components, so we only pass in a 2 here. And again, we're not doing any kind of striding or offsetting. So we've done a fair bit there. We've created another buffer. We've bound it within the draw scene. We've grabbed the location of the attributes that we need. And we've passed in this array of coordinates here. We've updated our shader to include another attribute for the texture coord. And we've told it that we want to output that in each vertex iteration. We're going to take it in here, use the coordinates that are passed to choose the texel from the texture, and then we're going to set that as our output texture. Our output color. So let's go and do a refresh, and we'll see. We'll bring the console up. We'll see what happens. So this obviously has gone horribly wrong. So GeoDrawRaid, attempt to access out of range vertices in attribute 1. So again, this is a zero-based array, so we know that what we've actually done is here we've gone out of bounds. This would be attribute 0, this would be attribute 1. So what I suspect has happened is I've sort of miscalculated somewhere. If you guys spot it, feel free to put it in the comments. We've got 6 textures there. We've created our buffer. We pass that in. Oh. We apparently had a bug from the start. Aha! There we go. So the reason that was working is here, what that would equate it to would have been 0, and we wanted it in slot 0 anyway, which is why the bug didn't show up to start with. Whereas when this should have been effectively 1, obviously that wasn't working. So that was a typo there, just trying to pull the correct variable. And you'll see that we've now got our texture on screen. We've got a warning down here about an invalid parameter name. So let us just pop back up to our textures and see what it is that is misbehaving. And that's what it is. It's not Y, it's flip Y, which also explains why this is upside down. So there we go. We've now got our rendering quad, our quad that's got WebGL on it, and you'll see that it pretty closely matches. The reason why they don't match is because I've changed the origin of this on the final one, so that it's in the middle. And we have this rotating around. We can speed that rotation up a little bit by rotating a bit more. And let's go ahead and just change the origin of that quickly. So all I'm doing here, instead of it being from 0 to 1, is now minus 0.5 to plus 0.5. Just check I've got that right. I've probably completely and utterly messed that up. So let's see what hilarity ensues. Aha! It hasn't. Brilliant. So now we'll see that this matches exactly what we were going for, just rotating a little bit quicker. And that pretty much concludes the end of this this tutorial. That was just the basics that I wanted to get going. Sort of a bit of a framework for you to see how things are done, get things started. Does anyone have any questions? Wait for the horrible Twitch lag. No, no questions? I guess I must have done such an amazing job of explaining it that no one has any questions, or you're all completely and utterly lost because I was a terrible teacher. So, as I mentioned at the beginning, the next workshop should be on the 12th of November, and we're going to dig into sort of colors and shaders a bit more, maybe get some multi-texturing going on, some vertex colors going in. And it's going to be 2 weeks today on the 12th of November at the same time, 7 p.m. In the meantime, if you've got any questions or any feedback at all, would appreciate all feedback. My Twitter is @LeadHyperion, or drop me an email at asa@zerodependency.co.uk, and I look forward to hearing from you all. Thank you very much, and good night.